Okay, so today we're going to cover chapter 6, section 3. Today we're going to learn about medians and altitudes of triangles. So the first thing we're going to do is define what a median is. Okay, so first we're going to define what a median of a triangle is. And a median of a triangle is going to be a segment from a vertex to the midpoint of the opposite side. In this figure, only one median is drawn in here, and it's the red segment. However, every triangle has 3 medians, and the medians are going to all be concurrent. So let me go ahead and draw in the other medians. So again, remember the median is drawn from the vertex to the midpoint of the opposite side. So if I wanted to draw the median out of vertex A, I would need to look for the midpoint over here of the side opposite, and then I would connect the segment to that. Remember, since this point is the median, I could call this point F. Then I know that that's going to be the midpoint. And I know that BF and CF would be congruent. And then if I wanted to draw another median coming out of vertex B, I would need to find the midpoint. And if I were asking you to calculate a midpoint, I would be giving you coordinates. Let me fix that so I can intersect it. And I could call this E, and again, it would split this into congruent segments. I know it looks a little off, but no, it's supposed to be hitting at the midpoint, which then would make EC congruent to AE. So the point of concurrency we're going to see on the next slide is going to be called the centroid, but we're going to get to that in a minute. It's where the 3 medians intersect. So again, a triangle has 3 vertices, so it also has 3 medians. So the point of concurrency of the 3 medians is called the centroid of the triangle. And just like the incenter, the centroid is always inside the triangle. So just to recap what we've already covered, let me just finish the slide. But the centroid is also called the center of gravity because it's going to be the point where a triangular region would balance. Now, over the last 2 sections, we learned about perpendicular bisectors and angle bisectors, and we learned their points of congruency. So remember the perpendicular bisectors, their point of concurrency was called the circumcenter. And remember, for the circumcenter, it could either be located in the triangle when it's acute, it could be located on the triangle when it's a right triangle, or it could be located outside the triangle when you have an obtuse triangle. Then the other segment that we learned about already was the angle bisector. And remember, its point of concurrency is called the incenter. And just like the centroid, it is located always inside the triangle. You're going to need to memorize all of this. So the next slide has the centroid theorem. And this theorem states that the centroid of a triangle is going to be 2/3 of the distance from each vertex to the midpoint of the opposite side. The medians of this triangle ABC are all meeting at point P, which is the centroid. And then the length of AP, which is the segment that comes out of the vertex to the centroid, is going to be 2/3 the length of the entire median. And then from the centroid to the side of the triangle, that is going to be the 1/3 portion of the median length. So let me go ahead and show you what I'm talking about. Notice that all of these point D, E, and F are all midpoints. So when it comes out of the vertex, so coming out of vertex A, or vertex A, this is going to be the 2/3 length of the entire median. And then when it continues after point P to the side of the triangle, this is going to be the 1/3 portion. And this will happen coming out of each and every vertice. So coming out of vertice B, vertice to the centroid is the 2/3 part. And then from centroid to side, that'll be the 1/3 portion of the median. And then the same thing coming out of vertex C. Coming out of the vertex is the 2/3 portion. And then finishing up from the centroid to the side is the 1/3 length of the entire median. This is the only segment in the triangle that doesn't produce either congruent segments itself or congruent segments to either the sides or the vertices. It's going to be 2/3 the length and 1/3. Now, do not be tempted to work with these as decimals, because 1/3 and 2/3, if you turn them into decimals, they're repeating. So you will need to work with these as fractions. So again, just to summarize what I just said, that out of the vertex, so coming out of the vertex to the centroid, the length of that piece is going to be 2/3 of the length of the entire median. And then when it goes and continues, and it goes from the centroid to the midpoint of the side, that's going to equal 1/3 of the length of the whole median. Example 1, it wants us to find the length of LS. Now, it's giving me that S is the centroid and RL, so this segment right here, this whole thing is equal to 21. So its whole length is 21. And then it wants me to find the length of LS. So remember, the length that comes out of the vertex to the centroid is the 2/3 portion. So in order to find LS, I know that the length of LS is going to be 2/3 the length of the whole thing, which was RL. I'm going to replace RL with what it equals, which is 21. I can put 21 in here as a fraction by adding a 1 to the denominator. Now, you can either choose to multiply straight across and get 42/3, but I'm going to simplify on the diagonals on this one. I'm going to simplify the 3 and the 21 and change this to a 1 and a 7. So the length of LS is 2 times 7, and it's 14. Now, let's say the question instead said to find RS. So RS is the 1/3 portion. So I could have also done RS equals 1/3 RL. And RS equals 1/3 times 21/1. Again, I would simplify diagonally here. And I'm going to make this a 1 and a 7. So RS is equal to 7. Remember, both segments added together need to equal the length of the whole thing. Now, another way we could have also found RS is if I've already found LS and I knew the length of the whole segment was 21, I could have just taken what I found, subtract it from the whole length, and then that would have given me RS that way. So this would have been RL, this would have been LS, and then it would equal the remaining piece, RS. Now we're going to do part B, and it wants me to find the length of NQ. So for NQ, NQ is this whole length here. But what they gave me was SQ, this little piece right here. And notice it goes from the centroid to the side. So this is the 1/3 portion. So what I'm going to do for part B, I want to find NQ. So I know that 1/3 of NQ, the whole thing, is going to equal SQ. So I'm going to replace SQ with what they gave me, which is 4. And now I have to apply my algebra skills. I can either show that I'm dividing by 1/3, but if you remember, divide by 1/3 really means multiply by the reciprocal. So I could do that over here. This cancels, and NQ equals 12. Now, if it wanted NS, the 2/3 portion, what I could do is I could just take the whole length that I just found, subtract out the piece they gave me, and 8 would have been NS. For example 2, it says a sculptor is shaping a triangular piece of iron that will balance on the point of a cone. At what coordinates will the triangular region balance? We are trying to find the order pair for the centroid. So remember, the centroid goes from the vertex to the midpoint of the opposite side. So what I'm going to do is calculate the midpoint of this side. So I'm going to go ahead and take the 2 order pairs, the 6, 6, the 8, 2, and I'm going to calculate the midpoint by adding the x's and divide by 2, adding the y's and divide by 2. This is going to give me 14/2 and 8/2. So the midpoint is going to be 7, 4. So I could graph that right here. And then I can draw the median into the vertex. Then I need to find the midpoint of this side. Do this one in, let me do it in gray here so it shows up better. So that side, I'm going to go ahead and take the 2 order pairs, the 10, 7, and the 6, 6. I'm going to find the midpoint, add the x's, divide by 2, add the y's, divide by 2, 16/2, 13/2. This will give me the order pair 8 and 6.5. So I can go ahead and find that order pair. Right here, draw the median from the vertex to that midpoint. And then lastly, I need to find one more midpoint and draw on that last median. So I can do this one over here. And again, those 2 order pairs are 10, 7, 8, 2. 10 plus 8, divide by 2. 7 plus 2, divide by 2. 18/2, 9/2 gives me the order pair 9, 4.5. So I'll go ahead and plot that one. And then I can draw in now my last median. Notice my point of concurrency is right here where the 3 medians intersect. And I can see that that is the order pair 8, 5. Now, the problem with this is if your graph isn't nice and neat, or even if your graph, let's say your centroid is actually a fraction, you won't know if it's 1/3, 2/3, 1/2. So this is where my trick using calculations is going to be a lot easier than having to graph it. But if the question said find the medians or draw in the medians by finding the midpoint, then you would have to do it what I just showed you. However, if it's only asking you to find the centroid, all you're going to do is take the 3 order pairs, 6, 6, 10, 7, 8, 2. And basically, you're going to find an average of the x's and an average of the y's. So you're going to take all of the x's, add them, divide by 3, because you're adding 3 numbers. Then you're going to take all of the y's, you're going to add them, and divide by 3. So once I add all those x's, I get 24 over 3. Once I add all the y's, I'm going to end up with 15 over 3. And then once I simplify, the coordinates of my centroid are going to be 8, 5. Because 24 divided by 3 is 8, and 15 divided by 3 is 5. And this is the coordinates for your centroid. Remember, the centroid is always located inside the triangle. So this trick works for no matter what type of triangle they give you. If it only asks you to calculate the centroid, add the x's, divide by 3, add the y's, divide by 3, and you're done. So next we're going to talk about an altitude of a triangle. So an altitude of a triangle is the perpendicular segment from a vertex to the line containing the opposite side. Every triangle has 3 altitudes. An altitude, just like the perpendicular bisectors, can be inside, outside, or on the triangle. An altitude is also known as the height of the triangle. So if you think back to your middle school days where you were asked to find an area of a triangle, remember the height was always next to the right angle. So in the first triangle on the left, notice the altitude is inside the triangle. However, the triangle on the right there, the altitude is outside of the triangle. So again, it's going to be that perpendicular segment from the vertex to the line containing the opposite side. Just like the other segments in the triangles, there are 3 altitudes in each triangle. Next, we're going to talk about the point of concurrency of the altitudes, and that's called the orthocenter. The lines containing, in this picture, AF, BD, CE are all meeting. Those are all the altitudes. All the altitudes are the red lines here. So all of the red segments are the altitudes in this particular figure. And they're all meeting at point G, which is the orthocenter. Notice this is an acute triangle, and the orthocenter is inside the triangle. Okay, so the first thing we're going to do is graph the ordered pairs and create our triangle XYZ. After we graph it, then we're going to find the orthocenter. So let me go ahead and graph ordered pair X. It's -3, -4. Then I'm going to graph Y, which is -3, +4. And then finally Z, which is at +5, +4. Notice when I connect my points, I'm creating a horizontal line and a vertical line. That tells me together that horizontal and vertical will form perpendicular lines. So this is a right triangle. When you have a right triangle, the orthocenter is always on the triangle. So this is a fact you're going to memorize. So when it's a right triangle, the orthocenter is on the triangle. And it's going to be located at the right angle vertex. So my orthocenter is going to be the ordered pair for Y. It's going to be -3, 4. Because when it's a right triangle, this leg is going to be an altitude. So the legs are the altitudes of the triangle. So this is also an altitude, because remember, it's going to be the segment that goes out of the vertex, and then it's the perpendicular segment. And then I can also draw another one here. So these are two altitudes. The third altitude, I can draw the perpendicular segment coming out of that last vertice. This would be the last third altitude that's drawn here. But the main thing you need to remember from this is the orthocenter, when it's a right triangle, is always located at the right angle. So it's going to be that vertice of the right angle. The two legs are always going to be altitudes. The orthocenter, when it's a right triangle, is always going to be located at the right angle, at the vertex of the right angle. So that vertex order pair is -3, +4. So in this picture, X, Y, and Y, Z, these are the legs, and they're also altitudes. The third altitude, you would have to draw the perpendicular segment down yourself. But as soon as you find the point of concurrency of two of them, the third one is automatically going to meet there as well. So again, remember, when it's a right triangle, the orthocenter is always on the right triangle, and it's located at that right angle vertex. Right. The next slide is just again showing you the location of the orthocenter, and that all depends on the type of triangle. It's the same as the perpendicular bisectors. When it's acute, it's inside, and when it's right, it's on it, and when it's obtuse, it's outside of it. All of the red lines in this picture are altitudes. And then the last slide is a summary of all the segments we've already talked about. We first talked about the perpendicular bisectors. So it's got the name in the first column. It's got an example of the segment in the second column. The third column has the point of concurrency. The fourth column has the property or the theorem that you can apply. And then the last one is an example showing you the congruent pieces and basically what it looks like. So a nice little summary of the 4 segments that we have covered.